Welcome to AP Physics Made Easy. If you're looking for help in physics, especially AP Physics, you've come to the right place. My name is Eric Sampson, and I am here to help you. Let's get started with this episode here. We're going to be talking about acceleration. So acceleration is simply the rate at which an object changes its velocity. So I'm going to start off with a car here that at time t equals 0 is going 0 meters per second. So the light turns green, the person hits the gas pedal, so at time 1 second, they're going 5 meters per second. T equals 2 seconds, they're going 10 meters per second. T equals 3, they're going 15. You've probably already figured out what the acceleration is, but let's just work our way through it using the equation. The equation for acceleration is this. Acceleration is equal to delta V over delta T. Remember, delta means the change in, and that means the final minus the initial. So I'm going to expand this to look like this. So my final velocity, which is 15, minus my initial velocity, which is 0, divided by the time it took to implement that change. And what I'll get is 15 meters per second minus 0 meters per second over 3 seconds. And I get 5 meters per second, which seems kind of weird. But think about it this way. What if I was talking about miles per hour? So I change my speed 5 miles an hour each second. So that doesn't sound so strange, miles per hour per second. Well, if I just change it to meters per second, that sounds a little bit weird, seconds per second. But so instead what we're going to do is we're usually going to compress this and write it this way. Mathematically, it's the same, so we're going to call it meters per second squared. All right, let's try this one here. Ready? I got my car at time t equals 0. It's going 10 meters per second. It's not starting from rest this time. And at t equals 5 seconds, it's still going 10 meters per second. But at t equals 6 meters per second, it's reduced its speed to 5 meters per second. And at t equals 7 seconds, it has come to a stop. So let's find the acceleration for this time period here between time t equals 0 and t equals 5. So what I'm going to do is I'm going to use my equation for acceleration. Remember, delta means final minus initial. So that's 10 minus 10 divided by 5. Well, clearly that's going to be 0. That means its acceleration was 0. So sometimes students get confused between velocity and acceleration. You can be going very, very, very fast and not be accelerating at all. When you're traveling in a jet, you might be going, I don't know, say 250 meters per second, but your acceleration is 0. All right, now let's look what happens here. So let's look at the acceleration during the time period t equals 5 to t equals 7 seconds. So again, I'm going to use this equation. Again, this means final minus initial. This means 0 minus 10. All right, so that gives me negative 10 divided by, and here is why it's important to always think of this not as t, and I'm lazy, I often write t, but really it's delta t, because what was my final time? My final time was 7. What was my initial time? It was 5. So a mistake students sometimes use is they just use this number here for t, but really it's delta t. So it didn't take 7 seconds to slow down and stop. It took 2 seconds. And that means the acceleration in this case was negative 5 meters per second squared. Now there's a common problem that you get in the AP Physics test where you have a ball that's placed in position A at the top of an inclined surface. Let's just say that from here to here is 6 meters. It rolls down, and after I release it, it gets to the bottom in 3 seconds, and I want to know what the ball's acceleration is. All right, well, I've been teaching this for like almost 40 years now, and I've seen students make a lot of mistakes, and this is such a common mistake that kids make. Please don't make it. What kids want to do is they say, well, I know how far it went, 6 meters. I know the time was 3 seconds. So they just go, okay, 6 divided by 3, and then I'm just going to divide it by time again because it's meters per second squared. But that's not how you do this. Do not make this amateur mistake. Let's see how you actually do this. What you want to do is you want to use the acceleration equation to find the instantaneous velocity at the bottom of the ramp. All right, that's what I need to do. So how am I going to do this? Well, I'm going to find the acceleration using just the distance and the displacement and the time. So I know how far it went and I know how long it took, and I want to find what the acceleration is. But to do that, I need to know this instantaneous velocity, not the average velocity. So I'm first going to find the average velocity. So average velocity equals the displacement divided by time, which gives me 2 meters per second. So on average, its velocity was 2 meters per second. But it started off at 0, and it ended up as something faster. So I can't just use this value here. That's the mistake students often make. Instead, I'm going to tell myself this. Well, any average means, like if I want to average two things, I just add up the two things and divide by 2 because that's how many things there are. So V average could be velocity 1 plus velocity 2 divided by 2. So in this case here, I would say my average, which I know was 2 meters per second, 2 meters per second. That was what my average is. I don't know what I know that my initial velocity was 0. I don't know what my final velocity is, but when I divide it by 2, I'll get this. So therefore, I can see that my final velocity is 4. Here's the big takeaway. You right? You ready? So when you have a problem like this, use your average velocity to find the average velocity as it goes down there. And as long as it starts from rest, all you have to do is double it. Multiply it by 2. Take the average velocity, multiply it by 2. That's the final velocity. It's a really good trick to know. Once I know the final velocity, which in this case is 4 meters per second, I can now find the acceleration because I know it took 3 seconds to go from 0 to this, and I can see that my acceleration, oops, I don't know why that happened, let's go back, okay, my final acceleration would be 1.3 meters per second squared. Sorry for that amateur mistake I just made. All right, one thing that's really important to keep in mind is that acceleration is a vector quantity, so direction definitely matters when we're dealing with acceleration. And this is something you need to pay attention to because a lot of students get into trouble with this. So let's just say I have this car at t equals 0 is going 10 meters per second, and at t equals 4 seconds is going 30. Okay, so the object is speeding up in the positive direction. So it's going in the positive direction. And it's speeding up. So speeding up in the positive direction means you have a positive acceleration. And I can prove that to you, right? So I'm just going to use the acceleration equation. I'm going to say the final minus the initial divided by the time gives me positive 5 meters per second squared. Well, an object speeding up in the negative direction is experiencing a negative acceleration. So here I have this car is going 20 in the negative direction, and 3 seconds later it's going 50 in the negative direction. It's speeding up in the negative direction. That means it has a negative acceleration, and we can prove it using this equation. My final was negative 50. My initial was negative 20. It took 3 seconds, and that gives me negative 10 meters per second squared. And now if an object is slowing down in the positive direction, so I start off going 30 in the positive direction, now I'm going 10, well, it's going to be a negative acceleration. So acceleration is going to be my final minus my initial. And then when I divide it by the amount of time, I get negative 4 meters per second squared. I think you see where we're going with this. So an object that is slowing down in the negative direction is experiencing a positive acceleration. So again, mathematically, I can show you that my final was negative 20. My initial was negative 50 divided by the time it took to implement that change, and I'll get a positive value here. So it's accelerating at positive 3, even though it's moving in the negative direction. What if I don't change my speed, though? What if the magnitude of my velocity doesn't change? I have a car that's going 20 meters per second, let's just say north, and now it turns, and it's going 20 meters per second to the west. But it never changed speed the whole time. It's like you driving a car at a constant speed on cruise control as you turn. Well, acceleration is a vector, and vectors have a directional component, and that directional component changed. So this object is accelerating in this case. This is what we call a centripetal acceleration. It's something we'll study later in the year, but just keep in mind that if you change either the magnitude or the direction of your velocity, you are accelerating. Okay, so look at what I have here. I have an object that's traveling in the positive direction, and it's accelerating in the positive direction. So that means if the acceleration is positive and the velocity is positive, then it's going to end up going faster, right? So the velocity vector is going to increase in magnitude because the acceleration is working in the same direction. However, if the object was traveling in the positive direction, the velocity was positive, but the acceleration was negative, then what's going to happen is the object is going to slow down. Okay, well, if the acceleration is opposite the initial velocity direction, what's going to happen? Well, the object is going to slow down, eventually stop, and then pick up speed in the direction of the acceleration vector. So here I have an object that is initially traveling at 10 meters per second in the positive direction while experiencing an acceleration of negative 5 meters per second squared. All right, so what happens 1 second later? So if it's slowing down at negative 5 and it's going 10, 1 second later it's going to be going 5 meters per second in the positive direction while still accelerating at negative 5 meters per second squared. Now a second later, it's going to lose another 5 meters per second, and so it's going to be going 0. So look at this. At this time here, which we'll call t equals 2 seconds, the velocity is 0, but the acceleration is still negative 5 meters per second squared. It's still accelerating in the negative direction, even though its velocity is 0. So just because your velocity is 0 doesn't mean that you've somehow stopped accelerating. You are still accelerating, it's just you're there for a moment in time. And 1 second after that, you're going 0, you're accelerating at negative 5, so you're going to be going negative 5 meters per second in the negative direction, and then 1 second later you're going to be going 10 meters per second in the negative direction. Well, let's talk about this really famous experiment that was performed in the 1500s by this really brilliant, cool guy called Galileo Galilei. Lived in Italy. This is the Leaning Tower of Pisa. I'm sure you've heard this story. I'm not going to go into it too much, but basically, people for thousands of years believed that objects that are heavier fell to the ground faster than objects that are lighter. You just say, well, look, I drop a feather, I drop a rock, the rock gets there first, the feather gets there second. See? But Galileo was the first person to really do actual experiments and collect data and analyze it, and he realized that this wasn't true. He said, no. If I drop two things, they're going to accelerate at the same rate. It turns out the reason the feather falls slower is because there's other forces, frictional forces, acting on both the rock and the feather, and they just have more effect on the feather than they do on the rock proportionally. Be that as it may, here's the point. Galileo apparently gathered a bunch of observers and who were expecting the heavy one to land first, and instead they both landed at the same time. Of course, they said you bewitched the heavy one to fall slower than it should have and didn't believe him anyway. But here's the thing. He came up with this idea that all objects that fall on Earth are going to accelerate downward at the same rate. And this is a true statement as long as I said before, we can ignore the effects of drag force or air friction acting on the object. And for most objects over short distances, we certainly can, certainly like in our classrooms when we're doing labs. So we're going to use this little letter G to represent gravitational acceleration because it's so often the case that the accelerations we see are being caused by the gravitational force. So this little letter here is something you're going to see so much this year. So let's just get used to it. Little g, technically what it means is the gravitational field strength, something we'll study later in the year. But for right now, we're just going to say it just means the rate at which something accelerates because of gravity. Now, it's a known amount. It's been measured. And so I think many of you come into this already knowing that the value is negative 9.8 meters per second squared. But I want to point something out to you, and this is really important, so please pay attention. This is just rounding it to two significant figures. That's not really what it is. It's like people have measured to a lot of figures, so let's just take it to 6 significant figures. We'd actually get this, right? Well, so this does round to this. Some books will say that's 9.81. We'll do 3 significant figures. But here's the thing. What, you think you're going to impress people by how many digits you've memorized little g for Earth? I mean, that's silly. College Board has a better idea for you, and you really need to accept this and lean into this. It will make all the difference in your success this year. We're going to round it to 1 significant figure. And by the way, significant figures are not considered in the AP test. You do not at all have to worry about how many significant figures you round your answer to. But look at this. They're going to say, we want you to learn physics instead of significant figures. Let's just round this to 10. So for 2% difference between this and this, actually less than that, we get something that's way easier to work with. So the idea is if you use 10 for little g on Earth, you will learn physics. If you insist on using 9.8, you're not going to learn it as well. And I'll show you why, okay? So this is why it's better to use negative 10 rather than negative 9.8. So let's just say a rocket is dropped off a building. At t0, it's released. And I want to know, well, how fast is it going after it fell for 3 seconds? So at t equals 3 seconds, how fast is it going? It is so easy to do this if I use 10. So if I use negative 10, I don't even need a calculator. It's going to be going 30 meters per second because for each of the seconds that it fell, it accelerated by 10. So 10 times 3 is 30. I can do that in my sleep. But try to do that in your head using 9.8. Quick. What's 9.8 times 3? Sorry, I went right past it. It's negative 29.4. My point is this. It's so much easier to learn physics if you use 10. And who cares if it's really 9.8? Because it's not really 9.8. It's 9.80665 and so on, okay? So use 10 and you'll do great in this course. Let's look at this here. I've got an object that's moving up at 50 meters per second in the upward direction. And let's say it's a cannonball. And I want to know, well, how fast and which way is it going to be going 8 seconds later? Well, the way I'm going to answer this is I'm going to use the acceleration equation. I'm going to say delta v would be final velocity minus initial velocity. I'm trying to find the final velocity. So I'm just going to substitute in the values that I know here. Okay, so acceleration, I'm going to use -10. The negative is going to be very important because it's traveling in the positive direction. It's accelerating in the negative direction. So it's going to slow down, stop, and turn around, it turns out, because I'm going to subtract its initial velocity, which is positive 50, divided by the amount of time. So when I multiply this across, I'm going to get negative 80, to which I'm going to add 50, and that gives me negative 30. So it's going to be traveling at 30 meters per second in the negative direction. So that's why paying attention to the positive and negative really helps. Now, usually we're going to use -10. It turns out we don't always have to use -10. As we go through the year, we're going to see a lot of times we're going to choose not to. So let me just point this out and I'll let it go, okay? So if I was to go around the planet and drop rocks, I'd see they all accelerate at 10 meters per second squared. But are they all accelerating in the same direction? The answer is no. Like these two accelerate in opposite directions. These two accelerate in opposite directions. So why does it have to be negative? And the answer is it doesn't. It's just often a little bit more convenient, especially if the thing goes up and comes back down. But the thing is, there's nothing inherently negative about the direction that gravity pulls things. And so you are welcome to, and in fact encouraged to. As always, thanks for watching. If you like this video, remember, like this video. Consider leaving me a comment. If there's some video you'd like me to make, I'd be happy to do that. Or maybe you could just give me some feedback on how to improve. You might want to check the description below to see if there's some links I've included that could help you out. And of course, as always, I would really appreciate it if you would like and subscribe.